Okay, now we're coming to another application of differentiation. That is for checking whether a function is monotonic or not, concaves up, down, or how to sketch, or and not or, and how to sketch the graph of a function using applications of differentiation. What does monotonicity means? We say that a function is monotonic if it is either increasing or decreasing or both. Okay, so monotonic functions, monotonic, monotonic functions are those are either increasing, I'll write it in a short way, okay, or decreasing, or both of them, okay, or not that plus between them, so that you will not confuse, so that it's not both increasing and decreasing. It is maybe increasing or decreasing or both of them. So how do we know that a function is increasing and a function is decreasing? We have got a procedure. Using that procedure, we can check whether a function is increasing or decreasing. In that section, later on, it has also talked about local extremas, okay, local maximum and local minimum. But I will put monotonic functions, the procedure for finding the monotonicity of functions and relative extrema together, okay, because it is just one step you added to the monotonicity. So what is the procedure for finding whether a function is increasing or decreasing? First, we are finding the first derivative of the function. First derivative. So we are finding f prime. Second, we are finding critical numbers. Okay. What are critical numbers? You know that a critical number is a number in the domain of the function such that f prime of x, that means the first derivative of the function, is equal to 0 or undefined. Okay, so that ones are critical numbers. I'm writing it like that. I'm not writing the procedure because you already know what is a critical number. 3, we are putting the critical numbers, okay? For example, we are finding A, B, and C, okay? The critical numbers that we have got, for example, they are A and B and C. We are putting those those numbers on the real number line. Sorry for that, not here. Put A, B, C on real number line. Of course, when you're putting that A, B, C on the real number line, it will subdivide the interval that you have got into intervals, okay? So if that is real number line, if I put A, B, C in here, what will I get? I will get sub-intervals on the real number line. Then I will choose test numbers, okay? What are test numbers? It's a number that I am choosing from that interval, because that interval is from negative infinity to A. So I will choose any number from that interval, and any number from A to B, any number from here, and any number greater than here. Okay, for example, I choose D, E, F, and G. Okay, so what's the step afterwards? I'm choosing test numbers from each subinterval. Then what are we gonna do? We're gonna put those test numbers into the first derivative of the function, okay? We are finding f prime of d, f prime of e, okay, f prime of test numbers, f prime of f, and f prime of g. Of course, you may have more than that test numbers, you may have less than that, but it's just in general talking about, okay, making it simple for you. If f prime of the test number, okay, is greater than 0, we say that f is increasing on that interval, okay? And if, of course, if I have got, if f prime of the test number is less than 0, of course it will not equal to 0, because if it equals to 0, it is the critical number. Then f is decreasing. Okay, so what do I have? I'm finding the first derivative of the function. I'm finding critical numbers. I'm putting those critical numbers on the real number line. Then I will have intervals. From each interval, I'm choosing a test number. Okay, then I'm putting the test numbers in the first derivative of the function. If the first derivative of the function is greater than 0, then it is increasing. Okay, if it is less than 0, then it is decreasing. For global, I mean for relative extrema, okay, that's step 6. If in the critical number, if how can I say that, if the sign, okay, changes at the critical numbers, then we have got a relative or local extrema. Okay, for example, if I have got a critical number here, and here is negative and positive, okay, look, that's the critical number. Okay, critical number. Of course, when you have got a critical number, you will check here is positive, negative, here is positive, negative, using this one. Okay, if it is from negative to positive, what does that mean? That means on the left side of the critical number, the function that I have got is decreasing. Okay, it is decreasing if it is less than 0, a negative number. Then on the right side, it is increasing. Since it is increasing, so the function will go up like that. So what will that point be? That point, if you look at it, it is the minimum point. Okay, so that one is relative minimum. How about if I have got a critical number, and on the left it is positive and on the right is negative? That means what? That means on the left side of the critical number, the function that I have got is increasing, and on the right side it is decreasing. So what will that point be? That will be relative maximum. Okay, relative maximum. How about if the sign doesn't change? If it is negative, negative, okay, or if it is positive, positive, what does that mean? The function is decreasing, decreasing, and that one is increasing, increasing. I do not have relative extrema. Okay, no relative extrema. So if the sign changes from negative to positive, I have got relative minimum, and if the sign changes from positive to negative, that means I have got relative maximum. We're given a function here. Sorry for that. 35. I'm given an example. We have got f of x that's equal to x to the power of 3 minus 12x minus 5. Find the intervals, although it doesn't say like that, but I will change the question. Find the intervals of increase and decrease. Then find its local or relative local extrema if exists, because we may not have local extrema, or we may not have the function increase, we may not have it decrease. Okay, maybe one of them occurs in the function. So what do I have? I'm given a function f of x that's equal to this one. It's required from us to find the intervals of increase and decrease, okay, monotonicity of the function, and local extrema if exists. So what do we have? What do we have to do? First, in the procedure, we have got finding the first derivative of the function. So I will start by the derivative of the function. That's the application of differentiation. What's the derivative of that function? That's equal to 3x squared minus 12. Okay, now what is the second step that we have to do? Let this paper be here, if you can see it. Okay, first derivative of the function. Then the second step, we have to find the critical numbers of that function. What are critical numbers? Critical numbers are those numbers that makes the first derivative of the function equal to 0 or undefined. So here, if you look at the first derivative of the function, I have got no point that makes it undefined. I just have got numbers. I can find numbers that makes the first derivative equal to 0. Okay, 0. So what does that mean? 3x squared minus 12, that's equal to 0. That is an easy example to do. Okay, what are the numbers that I have got here? I'm taking this 12 to the other side. Okay, let me write it here. 3x squared, that's equal to 12. I'm dividing both sides by 3 to get rid of that 3 in here. So I have got x squared is equal to 12 by 3, that's equal to 4. I'm taking a square root for both of the sides. So what will I get? I will get x is equal to positive or negative 2. Okay? So what are the critical numbers? These are the critical numbers, positive 2 and negative 2. Critical numbers. Okay? Now, since we found the critical numbers, here I found the first derivative, I found the critical numbers, then the third step is what? I'm putting those critical numbers on the real number line. So let's put those critical numbers on the real number line. I have got this, I will make it here so that I have got some space for later, okay, for finding increasing and decreasing monotonicity. I have got, of course, when I'm putting those numbers on the real number line, I'm putting them in order. I mean, negative 2 here and 2 there, okay, from ascending from smallest to greatest. So I have got negative 2 here and I have got 2 here. That is what? Putting the numbers A, B, C on the real number line. Then what do I have to do? I have to choose test numbers from each interval. How many intervals do I have here? I have got an interval from negative infinity to negative 2, that interval. I have got an interval that is between negative 2 and 2. And I have got an interval that is from 2 to infinity. So from each interval, I'm choosing a test number. A number that is less than negative 2, I can choose negative 3. You can choose negative 4, negative 5, or whatever number you want. But it is better for you to choose a simple number, okay? A number that's between negative 2 and 2. 0 is the simplest number. You can also, as I told you, choose other numbers. You can choose negative 1. 1 doesn't make a difference, gives you the same result. And the number that is greater than 2, I can put 3. I can take 3, I mean. Now, we did the first derivative, critical numbers, put them on the real number line. We chose the test numbers. What do we have to do next? We have to put the test numbers into the first derivative of the function to check whether it is increasing, positive, or negative, that is decreasing. So I'm putting those test numbers, okay? That means I have to find f prime of 3 numbers because I have got 3 test numbers here. I have to find the test number negative 3, 0, and 3, okay? When I'm finding those ones, I do not care about the value of this. That means if I put negative 3 in here, I'm not calculating it. Minus 3 to the power of 2, that's equal to 9. Multiplied to 3, that's equal to 27. 27 minus 12 is equal to, I don't know, 15. I don't care about the 15. I care about the sign, positive or negative, okay? So I don't care about the value, I just care about the sign, positivity and negativity of the function here. So let's put negative 3 into here. If I put negative 3 into the first derivative of the function, what will I get? I will get 27 minus 12. It is something positive. Okay, look, I just write it is positive. I don't care about the value. So whatever number I'm choosing from that interval, it will give me a positive number. So that interval is positive. What does that mean if it is positive? That means it is greater than 0. What does greater than 0 means? That means the function that I have got here is increasing. Okay, so I will do an arrow like that and I will write on it the function on that interval is increasing. You have to know these procedures because later on we will have curve sketching. If you will not know how to write increase and decrease, how is the arrow, you may make mistakes in the procedure. Okay, let's move to 0. If I put 0 into the first derivative of the function, 3 multiplied to 0, it is 0 minus 12, of course, gives me a negative number. Okay, what does that mean? That means whatever number I'm taking in that interval, it will give me a negative number. Even if you do one negative sign, it is enough. Okay, what does negative mean? That means the function that I have got, the first derivative, is less than 0. Less than 0 means that the function is decreasing. Okay, let's do the other one. If I put 3 into that function, 3 multiplied to 3 squared is 27 minus 12. That gives me a positive number. So here on that interval, the function is again increasing. Okay, here that function is increasing because the first derivative is positive. Now what do I have? Look, we found all that stuff. We found the intervals of increase and decrease. So from negative infinity to negative 2, the function, when I sketch the graph of it, will be increasing. And when I will look at the graph of the function, it will decrease from negative 2 to 2. And of course, it will increase again from 2 to infinity. Now, what is left to find? Finding the local extrema or relative extrema. How do I find relative extrema? I'm finding it looking at the critical numbers. Okay, so let us look at the critical numbers. Here is one of the critical numbers. Here is the other one. So local extrema occur at critical numbers. Let me see if this one is maximum or minimum. How do I know that if it is maximum or minimum? I will check. That side on the left, it is increasing, and then on the right, it is decreasing. So what is that point? It's a maximum point. So that one is relative maximum, or you can write local maximum. Okay, the same meaning. I'm coming to 2. On the left, the function is decreasing. On the left of 2, the function is decreasing. Then I have got the function is increasing on the right. So what is that point? That point is relative or local minimum. And that's all about the application of the first derivative of the function for checking the monotonicity of the function and finding the local extrema of the function. Okay, now another example is given. Look, if we had the sign not changing, we wouldn't have a local extrema. We have got another example. It says find the critical numbers. Example 2, of course. Find the critical numbers and identify the intervals of increase and decrease. Find local extrema of the function. But this one will be an exercise for you, although it is written for you. I mean, the solution is done there, but you can do it yourself. Okay? I will move to concavity and curve sketching. I'm coming to concavity. Okay. So the first thing that we studied, it was monotonic functions. Okay. Now I'm coming to concavity. What do I have in concavity? Concavity is to check whether a function is concaved up. Okay, if I have got a cup shaped, it is concaved up, or if I put the cup upside down, it will be concaved down. So in concavity, what do I have? In monotonicity, we had increasing and decreasing. In concavity, we have got concave up, and we have got concave down. Okay, in the first derivative we were talking about relative extrema, relative or local extrema. When we are talking about concavity, we will be talking about inflection points. Okay, points. So How do we check if a function is concaved up or concaved down? In general, we say that a function is concaved up if the first derivative of the function is increasing. Okay, we are finding the first derivative. If the first derivative is increasing, then we say that the function is concaved up. How do we determine whether it is concaved down? If the first derivative is decreasing. Okay, that is the general idea. But what is the procedure for finding this one? We will write it in the next page. Okay, what do we have to do? We have to find the second. Okay, I will write the procedure for finding the concavity of a function and inflection points, because I will make it into one subject because it is the same procedure. So first we have to find the second derivative of the function, okay, the first step. Then we are finding those numbers. Look, in the first derivative I was saying we are finding the critical numbers, okay, but here I'm saying we find those numbers in the domain of the function that makes the second derivative equal to 0 or makes it undefined. You can say the same thing here in the monotonic functions. When we say critical numbers, that means find those numbers that makes the first derivative equal to 0 or undefined. But we are calling them critical numbers here. But here it doesn't have a name. I'm just writing it. We are finding those numbers that makes the second derivative equal to 0 or undefined. For example, again, we get A, B, and C. Okay, so I will put those numbers, put A, B, C on real number line. Okay, like we did previously, but here we are working on the second derivative of the function. What is the first step? I'm choosing test numbers. Okay, choose test numbers from each interval. Look, it is the same procedure, but we are working on the second derivative. Choose test numbers. The fifth step is to find the second derivative of the test numbers. Okay, if the second derivative of the test number is greater than 0, that means f is concaved up. Okay, and if the second derivative of the test number is less than 0, that means the function that I have got is concaved down. Okay, and then what do we have? Inflection points. Where does inflection points occur? It occurs at those points that we find that the second derivative is equal to 0 or undefined. We are checking those numbers. If concavity changes, then the given numbers the given numbers that makes the second derivative equal to 0 or undefined, that we found in the second step, undefined, the given numbers are inflection points. If not, of course, it's not an inflection point. That's why I'm making it into one subject, because it is only one step further. Okay, going one step further. Let us do the first example, although it is very easy here. Let me check on another example. Okay, I'm having a function here, f of x. I think it's example 1, part A. I have got f of x that's equal to x to the power of 3. We will check the intervals of concavity for that function to check whether the function is concaved up or concaved down. Okay, for checking the concavity, what do we need? in the procedure we need the second derivative of the function. So let's find the second derivative of the function. F prime, first we have to find, that's equal to 3x squared. Then I have to find the second derivative because I'm working on the second derivative, that's equal to 6x. In the second step, it says find those numbers that makes the second derivative equal to 0 or undefined. I don't have anything that makes here undefined, so I'm finding those numbers that makes the second derivative equal to 0. Okay, so f double prime, I will set it equal to 0. That means 6x is equal to 0. That's a linear function, so x is equal to 0. So that's the ABCs that we found. And then what shall we do? We have to put those numbers, the number that we found. Okay, we found this one, but I'm not calling it a critical number here. It's just a number that I have found and makes the second derivative equal to 0. I'm putting that 0 on the real number line. Okay, since I put that 0 on the real number line, it gives me two sub-intervals, an interval that's between negative infinity to 0 and an interval that's between 0 and infinity. Then I'm choosing test numbers. A test number that is in that interval, I can choose -1, and a test number greater than this one, I can choose 1. Then what do I have to do? I have to find the second derivative of -1 and the second derivative of 1. Okay, that's -1, the test numbers. Look, the fourth step, we chose the test numbers. And the fifth step, I'm putting the test number into the second derivative of the function to check whether it is positive or negative, to check whether it's concave up or down. So I'm putting 1 and -1 into the second derivative. If I put -1 into here, what will I get? I will get a negative value. Again, here we do not care about the value, we care about the sign, positive or negative. So here, what did I get? I got negative numbers. What does negative number mean? That means the function is concave down. That means the cup that I have got is upside down, concaved down. Please write it down for me, concave down, because if you do like that, I do not know whether you mean it is concaved up or down, because there are students who make the mistake doing the cup upside down but writing it concaved up. I have seen lots of students doing that mistake. Okay, if I put 1 into the second derivative, what I will get? I will get something positive. Since it is positive, what does that mean? That means in that interval, the function that I have got, the cup, it will be a cup shaped up or faced up. That means that is concaved up. Why? Because it is positive. Positive means greater than 0. Greater than 0, that means it is concaved up. Now, I'm checking on 0. Okay, what have we found so far? We found the second derivative, those numbers that makes it equal to 0 or undefined. We put it on the real number line. We chose test numbers. We found the concavity of the function. And now I'm checking for the inflection point. Check whether I have got an inflection point or not. If I look at 0, okay, that's the number where I check the inflection point. If I look at 0, does concavity change from right to left? From left to right? Yes, it changes, because from the left side I have got negative, that means concave down, and from the right side I have got positive, that means concaved up. Since the concavity changes from down to up, so I will call this one an inflection point. Okay, and that is it for finding, or the procedure for finding the concavity of a function. Okay, here in concavity, I forgot to tell you why f prime is increasing. What does it mean? F prime is decreasing. When I say f prime is increasing, that means the slope of the function is increasing. How? For example, if I have got something like that, that's concaved up, if you see. And now if I have tangent lines, look, a tangent line is here, tangent line is here. Of course, I have got infinitely many tangent lines. The tangent line here, if you look at the tangent line is increasing. Okay, since it is increasing, that means f prime is increasing. So if the tangent line is increasing, that means it is concaved up. Here, when I say f prime is decreasing, that means the tangent line, or the first derivative, the slope of the tangent line is decreasing. Look, if you look at this one, it is like that, then it starts to fall. Okay, the tangent line that I have got starts to fall. Since the tangent line is falling, that means the slope is decreasing. What does that mean? Slope is decreasing. That means f prime is decreasing, and that means the function that I have got is concave down. I have got also curve sketching, but I will keep curve sketching for next lecture. I will explain that curve sketching because it takes time for an example to draw its graph. Okay, so I will leave it for next lecture, and I will explain it with indeterminate forms of L'Hopital, other applications of derivatives. So in that class, I mean in that section, what did we study? We studied monotonicity, that is increasing and decreasing functions, relative extrema, the procedure for finding increasing, decreasing, and relative extrema. We were using the first derivative of the function. We were working on the first derivative of the function. And then we came to the second part of section 3 of chapter 4. It is about concavity. In concavity, we were using the second derivative of the function, okay? Whatever we did the procedure, it was on the second derivative of the function. What does concavity mean? That means it is concaved up. That means if the cup that I have got is faced up or faced down. And we also found the inflection point using the concavity of the function. I hope you would have enjoyed watching that video. Hope you will understand again. Have a good time, and bye-bye.